In this video, we're going to talk about the logarithm transformation, which is one of the primary transformations that we're going to be interested in using in this section. So, we're going to use the logarithm transformation anytime we have data that appears to have an exponential relationship. We'll go over in just a second what an exponential relationship is going to look like. But anytime we see a pattern, like an exponential relationship, we're going to use those logarithms, take the logarithms of one of our data sets, our y variables, and that's going to allow us to transform the data and create a linear relationship between our values. But before we do that, we need to talk about properties of logarithms quickly. This is, again, some Algebra 2 review. First of all, when we're talking about logarithms are really just a special way to talk about exponents. So let's look at this equation first. If we have the equation b to the y power is equal to x, what that means, or we can rewrite this using this equation over here. And so instead of expressing this in terms of an exponent y, we can talk about the logarithm. For those of you who had me for Algebra 2 last year, you hopefully remember me showing you how to convert from an exponential equation to a logarithm equation. We made those little spiral shapes. So I'll do that again here just to jolt your memory. What I would always tell you, and what I'll tell you again here, is that you're going to start with your writing utensil on the base of the exponential equation. So in that case, it's b, right here. And we're going to draw our spiral around the equal sign, including the x, and then we're going to end up at the y. So again, this is just the order in which we're going to rewrite this equation to transform it from an exponential equation into a logarithmic equation. So because I started off at the base, that tells me that the log base b, which is what I've got right over here, log base b of x is equal to y. And that's exactly what we've got written in this equation over on the left. So any logarithmic equation we can transform into an exponential equation. And that is going to be something that we'll be doing in a bit when we're talking about how to write our logarithmic equations that we get from our transformations and to rewrite them as exponential equations. A couple of other things that you need to keep in mind. I just noticed a typo on the slide. This is number 4. Just a moment. There we go. It would help if your math teacher could count. A couple of the other properties of logarithms that we need to refresh on is, first of all, what happens when we take the logarithm of something that we're multiplying together, which is what we're doing right here. This property of logarithms says that we can split up this product, m times n, into two separate logarithms. We've got the log base b of m, and we add that on to the log base b of n. So again, if you've got a product of logarithms, you can split that up into a sum of logarithms. The third property is very similar to the second, only instead of multiplication, we're looking at what happens when you're dividing two things. And this property just says that if you're taking the quotient of two values and then taking the logarithm, you can split that up into two logarithms, and this time you're going to be subtracting the two. So again, if you are multiplying, you want to be adding the two logarithms, and if you're dividing, you're going to be subtracting the two. It's important to keep that distinction in mind. And then the very last property that we need to talk about is what happens when you have an exponent inside of a logarithm, which is what we have right here with this p. This expression would read the log base b of x to the p power. Anytime you have an exponent inside a logarithm, this property tells us that we can take that exponent and we can pull it out front so that it becomes a coefficient, which is exactly what we have over here on the right side of this equation. Instead of having p as our exponent, p is now being multiplied out front by the log base b of x. And notice that there is no exponent here anymore. It's just become 1 now. So these are 4 properties that you need to be comfortable with so that you can perform these transformations with logarithms successfully. Just quickly, I want to review that there are two commonly used bases in logarithms. Typically, we're going to use either the common log, which is a log of base 10. We also just write that log of x. We don't bother writing the base usually. And then we also have the natural log of x, which we abbreviate ln. That's really, if we want to write it out this way, that's the log base e of x. So most of the time, those are the only two logarithms that you're going to have to deal with in this class. Frankly, I can't imagine any situation where you'd need to worry about any other type of logarithm for our purposes. So I just want to go over how we're going to go from an exponential equation and transform it into a logarithmic equation. So here's the basic form of an exponential function. We've got y equals a times b to the x power. And because our variable x is up there in the exponent, that's what makes this an exponential relationship. But what we're going to do is we are going to take the logarithm of both sides of this equation, because, algebraically, anything you do to one side of the equation, you've got to do to the other. So we've got the log of y is going to be equal to the log of a times b to the x. I'll write some parentheses in here so you can really see what's happening. Now, using some of those properties that we just talked about on the last slide, we're going to be able to rewrite the right side of this equation. So notice here we've got ourselves a product, a times b, and we know that when we have the product of two expressions and we're taking the log of that, we can split that up into a sum of logarithms. So the right side of our equation then is going to become the log of a plus the log of b to the x. And again, all I've done there is used property number 2 on this slide. Then the next thing we're going to do is we're going to notice that, hey, we are taking the logarithm of something that has an exponent on it. And we know that from a couple slides ago that property number 4 says if we're taking the logarithm of something with an exponent, we can pull that exponent out front. So that's exactly what we're going to do here. So the left side of the equation is still the log of y. We still have the log of a. But now we're going to take the x, our exponent, in this equation, and we're going to pull it out front. So now we're going to have x times the log of b. And so what we've actually just done here is we've taken an exponential equation and we've transformed it into a linear equation, which is our entire goal. So let's talk a little bit about why this is suddenly a linear equation. Well, the log of y, that's just going to be the logarithm of all of our y values. That's still just a variable. A and b from our original equation, those are just constants. And so the log of a is going to be another constant. This is actually our y-intercept in the linear equation. And the log of b is another constant, and that's actually going to be our slope, because notice it's being multiplied by x. So this is really just the equation of a line in slope-intercept form, except we've written it oddly, and we've got these logarithms involved now. So I want to do a couple of examples, just so you can see a little bit better how this would actually work. So let's say we have this exponential equation, y equals 5 times 3 to the x, and we're going to go ahead and take the log of both sides. I'm going to take a common log here, just because on the next example we'll take a look at using natural logs, but you could use a natural log here. That wouldn't be a problem at all. So we're going to take the common log of both sides, so we get the log of y equals the log, actually I'll use brackets, the log of 5 times 3 to the x. And then using the exact same principles that we used in the example that I just did, we're going to split up this product here. We've got 5 times 3 to the x, and so we know that we can split that up to be just the log of 5. plus the log of 3 to the x. And then we also know that because we've got the log of 3 to the x, and the x is an exponent, I can pull that x out front, so this equation becomes the log of y plus the log of 5, the log of y equals the log of 5 plus x times the log of 3. And so just like we saw before, the log of 5 is then our y-intercept in the equation, and the log of 3 is our slope. We'll do one more example. This time notice that our base is e. And like I said in the last example, it doesn't really matter what type of log you use, but in this case, because we have a base of e, it makes more sense to use a natural log here than a common log, because the natural log has a base of e. So let's take the natural log of both sides. Remember, that's represented by ln. So we've got the natural log of y equals the natural log of 6 times e to the x. On the right side, we're going to split it up just like we did before. So we'll have the natural log of 6 plus the natural log of e to the x. And next step, we're going to pull that exponent of x out front. So this becomes x times the natural log of e. And one more little property of logarithms that we haven't specifically talked about yet, but it is that if you take the natural log of e, then these are inverse operations, so this is actually just equal to 1. Similarly, if you took the log base 10 of 10, those two functions cancel each other out, and that would just be equal to 1. If you took the log base 3 of 3, those two functions cancel each other out. So hopefully you see the pattern there. So that just means that our final equation would be the natural log of y equals the natural log of 6 plus x. So in this case, our y-intercept is the natural log of 6, and we just have a slope of 1.